So in this video, we're going to take a look at the homework that I assigned for continuity and a little bit on limits. So let's just jump right in, since this is a homework review. You certainly can scroll to the problems that you need, but I'm going to talk about probably all of them. There may be a few I don't talk about. So let's begin with number 59. In number 59, we are trying to find let's stop the video, let's start again. All right, in this homework video, I'm going to work out most of the problems for you, so feel free to scroll through for the problems that you need. I'm going to begin with problem number 59. And in number 59, we're trying to find the limit as x approaches 0 of this given function right here, which happens to be a very complex rational function. So as you know, the first thing I'm going to do is rewrite this so that we don't have what I call the slanty fraction bars. So I'm going to rewrite this as 1 over 3 plus x minus 1/3 over x. And then I like to put a 1 as my denominator, just like I did when I was back in 4th grade and I had a math problem like 3/4 divided by 5. That's the same thing as 3/4 divided by 5 over 1. And when I do that division, as you know, I'm going to rewrite that as 3/4 multiplied by the reciprocal, which is 5 over 1. So I'm going to do exactly the same thing over here on the left-hand side. Except for in this case, I have a fraction minus a fraction over a fraction. So I'm going to work first with the numerator. I'm basically going to ignore the denominator right now, because now I have to get a common denominator in the numerator. So if I come back over to 4th grade math, that would be doing something like 1/2 minus 1/3. So I would get the common denominator by multiplying 2 times 3, and I would carry out my 4th grade work multiplying the first fraction numerator denominator by 3, the second fraction multiplied numerator denominator by 2, and then moving forward from there. So I'm going to do the same thing here. I'm going to keep the limit because I haven't found it yet, so that's important. And the common denominator of the numerator would be the 3 from the second fraction multiplied by 3 plus x in the third fraction. So that's my common denominator. So I'm going to multiply the first fraction by 3. I've already done it in the denominator, and 3 times 1 is 3. Then I have the minus from right here. And then I'm going to multiply the denominator by 3 plus x and the numerator by 3 plus x, which means I'm really multiplying by the number 1. Be sure to put parentheses around that because you've got to distribute the negative. Now, as I said before, from 4th grade math, when we divide by a fraction, we multiply by the reciprocal. So I'm going to go ahead and change this into a multiplication problem, and the reciprocal of x over 1 is 1 over x. All right, now I'm going to carry through the algebra, and I'm going to distribute the negative and distribute the negative. So I know that 3 minus 3 is 0, and that leaves a negative x in the numerator over 3 times 3 plus x in the denominator multiplied by 1 over x. And so I still have the limit because I haven't found it yet. X approaches 0. So since I'm multiplying these fractions, I can remove the discontinuity. In other words, those two x's divide each other out. I still haven't found the limit. Let me scroll down here. Give me one second here. So I'm keeping the limit because I'm still doing the algebra work. So limit as x approaches 0. I have a negative 1 left in the numerator. And I have 3 times, there's no need to distribute that 3 in because when we find the limit, remember we're trying to find the y value being approached. So now that I've removed the discontinuity, I can use direct substitution, and that'll give me, now I drop the limit because I'm doing the work, that would give me 3 times 3. So the y value that is being approached, if we had a graph, we would see that the graph is approaching a y value of negative 1/9. So that's how you do that problem right there. All right, I'm going to clear the screen. I'm going to do a reset, and then I'm going to go back up to the top and do the next problem, which is pretty much the same problem with different numbers in it. If I were you, I reset my screen. Let's undo that. I took away everything. All right, so let's clear the annotations. And let's go to number 60. I think you can see that 60 is exactly the same as 59, except for now we have, excuse me, x plus 4. So if you had trouble with this, I would strongly recommend that you stop the video right now and you do this problem and prove to yourself that you can do it, because watching me do math doesn't necessarily make you any better. All right, so I did the same thing. I put a 1 in my denominator. I'm going to keep the limit because I haven't found it yet. That comes at the end. I'm going to get a common denominator for the numerator. So I'm going to multiply the x plus 4 by 4. So the common, I should have given myself a little bit more space. Let me slide that down a little bit. So there's my big fraction bar. So the common denominator in the numerator is 4 times x plus 4, and I'm making one fraction out of 2 by getting a common denominator. I'll change colors here. So the first fraction needs to be multiplied by 4. 4 times 1 is 4. The second fraction needs to be multiplied by x plus 4 in the numerator and the denominator. I already have it in the denominator. Notice I have another subtraction. Subtraction is very dangerous, so make sure that you put parentheses. And then I still have the x over 1. I'm going to change that into multiplication, and I'm going to multiply by the reciprocal of 1 over x. So I didn't really need the big fraction bar. All right, now comes algebra time. I'm going to distribute and distribute, and the 4 here minus 4, when you distribute that negative, makes 0 again. Distribute, and you get a negative x in the numerator over 4 times x plus 4 times 1 over x, and you can see that we have another removable discontinuity. So out and out. So now that leaves me with the limit as x approaches 0 of negative 1 over 4 times x plus 4. I can substitute the 0 to find the y value the function is approaching, and I would end up with negative 1 over 16. So that's the y value that this function approaches. All right, so that's the limit work that I asked you to do in this homework. Let's take a look now at the continuity work. As soon as my page turns. There we go. Nope, too many pages. All right. So this is not page 15. Depending on what year you're looking at this video, the homework page may not be the same, so I'm not going to quote the page number. It's this problem right here on whatever page it is in your packet for whatever year you are taking calculus. So in problem number 2, we're trying to determine whether or not the function is continuous, and if it's not, this is the important part. Why is it not continuous? What part of the there are 3 conditions, what part of the 3 conditions is broken to justify a discontinuity? So at a sub 1, we can clearly see that there's a jump discontinuity, but the problem doesn't say what kind of discontinuity. It says why, or how is the continuity broken. So the first condition of continuity is that there is a y value, and there's a y value right there. So far so good. The second condition of continuity is that the limit must exist. Well, if we come in from the left and from the right, it's evident that the limit does not exist, so I'm going to say the limit as x approaches a sub 1 of f of x does not exist. Now, I do not need to continue onward and justify why the limit does not exist, because this question is simply asking about continuity. It's not asking for the justifications of limits. If you did justify why the limit doesn't exist, and you did it correctly, you'd be perfectly fine. That would be legit. The function at a sub 2, so a sub 2 is right here, and there is a y value. The limit is an agreement from both sides, and the limit equals the y value, so we have a continuous function at a sub 2. At a sub 3, we can see here that there is a hole in the graph, so there's a point discontinuity there, and condition number 1 is there a y value? Well, no, there's not. There's an open circle, so I'm simply going to say the function at a sub 3 is not defined. Let's clear the board here. It's getting a little bit messy. At a sub 4, again, we can clearly look at the graph and see that there is a discontinuity. So let's go through our conditions. Condition number 1, is there a y value? Yes, there is, because there's the solid point. Does the limit exist? Well, coming from the left and coming from the right, the limit does not exist. Therefore, that's my reason why the function is not continuous at a sub 4. In number a sub 5, which is right here, there is a point discontinuity. There is a y value. There is a limit. But condition 3 says the limit must equal the y value. So that's the problem in this case, and I'm going to say the limit as x approaches a sub 5 of f of x is not equal to the y value or the function value f of a sub 5. And then we have continuity at problem number 6. Moving onward. So these probably were a little bit more challenging. I lost my mouse here. In the multiple choice section. So question number 1, which of the following functions is not continuous everywhere? Well, we know from prior knowledge that an absolute value function is a V shape. In this case, the vertex would be 0, 0. That is a continuous function, so we're good. Letter B is a rational function. I'm going to make some notes over here. B is a rational function, so I'm thinking maybe there's a vertical asymptote or a hole in the graph. However, when I look at the denominator is x squared plus 1. Well, x squared plus 1 cannot equal to 0. There's no number that I can square and add to 1 and get 0. So I'm not going to get a vertical asymptote, not going to happen. The numerator of this rational function, x, that doesn't factor, so I'm not going to remove a discontinuity. Also, I notice in the denominator, x squared plus 1 is always a positive number. Because even if we substitute 0 for x, we get 1. So squaring a number other than 0 always yields a positive output. Plus 1 is going to make that number even more positive. So that denominator is never going to be 0. So regardless of what that function looks like, it is going to be continuous everywhere. So that is another continuous function. In letter C, we have you might think it's a square root function, and it does have a square root on it. Let me get rid of some of this stuff. But I'm going to, if you don't know what that is, some of you may know what it is just because you remember it from a prior knowledge. But let's take this function back, or this relation. It's actually not a function. Oh, that's interesting. Oh, it is function because we're only, sorry, the top half. So if we get y equal to the square root of x squared plus 8. I'm going to square both sides to get rid of the radical, and I get y squared equal to x squared plus 8. And then I'm going to move the x squared to the left-hand side and get y squared minus x squared equal to 8. You may or may not remember that this would have to be a hyperbola. And a hyperbola, and it's only going to be half, by the way, it's only going to be half of the hyperbola, because in the original problem, the principal square root is the positive square root. So it's only one side of a parabola, not both. Therefore, it is a function. There is no value of x that you could not substitute in and generate a y value. Positive numbers are safe, negative numbers are safe, fractions are safe. So this function is continuous everywhere. Notice I'm using my reasoning and not necessarily making the graph. I'm trying to think of this the way that you guys might, because you might be going, I don't know how to graph that. X to the 2/3 power is a power function. Power function. Now you may or may not know what that looks like. So also, if we rewrite this as a radical, this is a good opportunity to do a rewrite. The denominator is going to be the index of the radical, and the numerator is the power. So think about this. Don't even worry about the square. Think about taking the cube root. you can take the cube root of every kind of number. You can take the cube root of a negative. Yes, you can. The cube root, think about it. The cube root of -8 is -2. You can take the square root of 0. You can take the square root of positive numbers, meaning that this function is going to be continuous everywhere because every x generates a y value. There would be no breaks, gaps, or holes. So finally, we get to letter E, and in letter E, this is a rational function, and if we set the denominator equal to 0, we get x equal to -1, and we know the denominator can't equal to 0, so there would be a vertical asymptote here. Therefore, this function is not continuous everywhere. Number 2, this one always gives students a little bit of trouble. So I'm trying to decide which of the following statements are true about this function right here. So the first question is f is defined at 0? Now this is where a lot of students have trouble, and they think that no, f is not defined at 0 because division by 0 is undefined. Well, I get that. But what this problem is saying is that for this graph, if we were going to produce it, we would substitute all values of x that are not equal to 0. And that keeps us safe. And then they say right here, for this graph, if we were to produce it, when x is 0, we're going to have a point. We're going to have the point 0, 1 on the graph kind of sitting out by itself. Now, I don't know if that's where the hole is or not. But there is a hole in the graph because if we factor, that's not x squared plus 1, that's x squared plus x. If we factor the numerator, we can factor out a common factor of x and get x plus 1 over x, and we have the removable discontinuity. So yes, indeed, there would be a hole or a point discontinuity at x equal to 0. However, because they are defining, this is defined, that when x is 0, there is a y value of 1, so that fills up that hole. So that can be a bit confusing. So yep, according to the given information, f of is defined at x equals 0. And the limit as x approaches 0 does exist because there's no vertical asymptote there, there's a hole in the graph. And f is, so therefore, since the hole and the y value equal each other, the limit and the y value equal each other, the function is continuous. So all of those actually apply. All right, let's move on to, let me give myself a little more paper down here. Let's move on to number 3. This is one of those mysterious functions that we're going to force to be continuous. We don't know what k is, but we're going to find a number that makes the function be continuous, that it will not have a hole in it. My breaking value is 0. So I'm going to substitute 0. Well, first of all, that numerator is begging to be factored again. I have a common factor of x. So that leaves me with x times x minus 1. The x's divide out, leaving me with x minus 1 over 3. So I'm going to remove the discontinuity. Then I'm going to substitute the 0 in here. And when I do, that gives me a value of -1/3. But right here it says, you can't really substitute 0 in there, so we're going to have to put a hole in the graph. That's why I put that to remind me that that's a hole, not really a y value. All right, then I'm going to go to the second piece of the piecewise, and I'm going to substitute 0 into the x, which really there is no x. So when x is 0, or for any value of x, the y value is k, and that's going to be solid. So that's what that looks like. So that's my specific point. So in order for the function to be continuous, the point has to fill up the hole. Well, the only way the function can fill up the hole is if these two y values equal to each other. So I'm going to set k equal to -1/3, and I really don't have to do any work to produce the value of k that I'm looking for, which is -1/3. Problem number 4. If f of x is continuous, meaning that we have 1, 2, 3 criteria, there is a y value, the limit does exist, and the limit equals the y value, which of the following may be true? Maybe, maybe not, but could be. And there's another way to say that instead of maybe. Could, or no, may be false. I'm looking for the one that may be false. Be careful. These things can be really tricky. So, since our function f is continuous, the limit as x approaches a exists because we have a continuous function. The limit exists everywhere, so that's why we have a true. C is the answer, so we'll go to B. The limit as x approaches a of f of x is equal to f of a. In other words, the limit is equal to the y value. That's from the definition of continuity, so it has to be true. Letter D, f of a is defined. That's from the definition of continuity. There has to be a y value, so that has to be true. Limit as x approaches a from the left side equals the limit as x approaches a from the right side. Well, we already said over here the limit exists, therefore the left and right limits have to equal each other, so that has to be true. This part right here, f of a is equal to f of negative a. That says if you were to have a graph and you have a x value of a and an x value of negative a, obviously they would be symmetrically located about the origin. This says the y value at, and we'll just say the y value, that would be f of a, equals the y value at negative a. Really, they're saying an even function. So which of the following statements may be false? Well, this might be false. I don't have to have an even function, but I might have an even function. Moving on to number 5. This is a forcing continuity. So I have 1, 2, 3, 4 pieces of a piecewise function, and I have a breaking value at 0, a breaking value at 1, and a breaking value at 2. So I'm just going to go x value by x value. So input 0, it's not equal to, the sign of 0 is 0, open circle, because not equal to. 0 substituted into x squared gives me 0. It has an equal to, so that's solid. So I have continuity because from the left and from the right, I'm approaching the same y value. So the limit exists, the y value exists, and they equal each other. I can see that right there. So that's good news. All right, now I'm going to move on to testing out 1. When I substitute 1 in x squared, I get 1, but it doesn't have equal to, so that's why I have the open circle. When I substitute 1 into the third piece, 2 minus 1 is 1. That has an equal to. That's solid. And so again, I notice coming from the left and right, I'd be approaching the same y value of 1. So the limit equals the y value. So we have continuity at x equal to 1. And then lastly, we're going to try it with 2. So 2 goes into the third piece. 2 minus 2 is 0. No equal to, so I have an open circle. 2 substituted into, the fourth piece. 2 minus 3 is negative. We got a problem here. The y values are not the same, so the function cannot be continuous at x equal to 2. And that brings us to our last page of this particular set. Again, the page numbers vary from packet to packet, year to year. So in number 1, I probably did this one in class with you. This is forcing continuity. I'm doing the same thing that I did in that last problem. I go to the breaking value, I substitute in 2 and get an output and say closed because of equal. I substitute 2 into x, I get 4a, open circle, because not equal, and to force the continuity to happen, the y values must equal. So that's why I'm setting those two y values equal to each other, and I solve for a, which means if a is 2, then this piecewise function will be continuous. If a is any other number, 3, 7, -1, 2/3, then I will not have a continuous function because I'll generate 2 different y values. I know B comes after B comes after A, but I'm going to move to the right instead. It doesn't matter which direction we move in. Same deal. Substituting -1 into this piece gives me 2. Close circle equal to -1 into the second piece in place of x gives me -a plus b. So since these 2 points have the same x value, they must have the same y value. So therefore -a plus b must equal to 2. Play the game again with 3. So I substitute 3, and set those y values equal to each other. And what I end up with is this. Well, from your Algebra 1, Algebra 2 days, that is a system of equations. And we have 3 methods by which we can solve a system of equations. The day I made this video, I did it with a class where I did I found the by elimination. But in this particular workout, I decided to use the substitution method to solve this equation. So I'm going to change colors here. I took -a plus b, and I got b by itself. So b is equal to 2 plus a. So I'm going to substitute the expression for b into the second equation, and I got to into the second equation, combine like terms. I solve for a to be -1, which is I get right here, and then to find the value of b, I'm going to take the -1 and substitute it into either of those 2 original equations to find the value of b. So in this case, if a is -1 and b is +1, then we have a piecewise function that would be forced to be continuous. This one's going to be tricky for you guys because depending on what year you did this, if it's COVID year, we didn't really talk about the special limits, so I'll go ahead and do it in any respect. So here we go playing the game. Actually, I'm not going to do it because this is designed for the COVID year. I'll do it in class for the folks who aren't in COVID year. I hope this ends soon. So in letter D, this is another one of those. You've got to look for situations where the numerator or the denominator is begging to be factored. So in the numerator, I have x squared minus a squared, which factors into x minus a times x plus a. Make sure your algebra is sharp. So that's where I got that from in the numerator, and then I can remove the discontinuity. Then I can substitute a into my leftover. So a plus a is 2a, so that's where that came from. And then I'm going to substitute a in place of the second piece, which is a constant function. So when x is a, y is 8, and that is my solid because it has the equal to. Therefore, this solid needs to fill up the circle. So these 2 y values have to equal each other, so a would need to be 4 in order to force the function to be continuous. And then there are 2 more of these that are pretty much the same thing. I think you can follow the pattern from here. So I hope this helped you with homework. And if you still have questions, you can ask me in class or during an extra help time.